cutoff region, then linear region, जिसको आप ट्रायोड रीजन कह रहे हैं, and then saturation region, right? And so these regions, we have a different current equation. For example, here this region is actually characterized by VGS less than VTH, right? And this implies that the current is zero. Similarly, linear region is characterized by VGS greater or equal to VTH. Of course, the transistor shall be on. And what is the requirement for VDS? VDS shall be less than or greater than the overdrive voltage in linear region.
Yes, sir.
It shall be less than VGS minus VTH, right? And this VGS minus VTH is also referred to as VOV. This is a very important terminology that you will be often referring to. This is referred to as overdrive voltage, right? So the term VGS minus VTH is referred to as overdrive voltage, and most of the time we will be talking in terms of the overdrive voltage. So you shall remember, what do we mean by overdrive voltage? Overdrive voltage of a transistor is given by VGS minus VTH, right? And similarly, the saturation region is characterized by, so of course the transistor shall be on, so VGS shall be greater or equal to VTH, and here VDS shall be greater or equal to VGS minus VTH. So VDS shall be actually greater than the overdrive voltage. Now, you have learned transistors earlier also, and electronic circuits can broadly be classified into two: digital circuits, they are also designed using transistors, and analog circuits, right? Digital circuits and analog circuits, both they use CMOS. They are CMOS circuits. Like digital circuit, you can have CMOS digital circuits. Similarly, you can have CMOS analog circuit. Now, what happens in digital circuit? Transistor is used as switch. Transistor is used as switch means either the transistor, so we refer to the operation of transistor as transistor is on, transistor is off, like this in digital circuit. We are not concerned like, or in fact, when the transistor is off, so it is in cutoff region, and when it goes from off to on, it starts in, say, saturation region and then ends in linear region, like that. But primarily in digital circuits, transistor is used as a switch, and we when we discuss the operation of transistor in digital circuit, we simply refer that, okay, the transistor is on and the transistor is off. Whereas in analog circuit, the transistor is always on. Transistor is always on. Means this implies that ID is not equal to 0. In digital circuit, when the transistor is off, ID is 0, and when the transistor is on, ID is non-zero. Whereas in analog circuits, transistor is always on, so ID is not equal to 0. You will always have current flowing through the transistor. Now, from the region of operation of transistors, we have just seen that there are two regions where the current is non-zero, the linear region and the saturation region. So now there is a question, in which region the transistor shall operate when you are designing an analog circuit, right? ID is not equal to 0 actually implies that you will never bias transistor into cutoff region when you are designing an analog circuit. But ID is non-zero for both the linear region and the saturation region, right? Do you remember the current equation? So I can write ID linear as half mu Cox W upon L, then 2 VGS minus VTH into VDS minus VDS square. Did I write it correct? Or do you want to correct me? Can you recall the expression for ID linear? Anybody? I'm not getting response for any of you. Is it a current? Is it correct? Yeah, when I'm asking you that is it correct, it is not that I'm always trying to test you. I may have made some mistakes, so you shall correct me.
Ishan, Ishan, answer yes or no. Answer correct or not correct?
Yes, sir, it is
Yes, sir, it
correct.
is correct.
Okay, thank you.
Actually, sir,
Z
friends are
is Z present?
pictures is the thumbs up mark. So yes,
So it is not that I'm always testing you. Sometimes I may miss something, so you shall be alert and just interrupt and correct me. ठीक है
Z
ना?
Tawheed, is it correct
yes, sir, it is
or
correct.
no?
Yes, sir, correct.
Okay, thank you. And then we have ID sat, which is given by half of mu Cox W upon L VGS minus VTH whole square, right?
Yes, sir.
So we have two regions of operation for a MOSFET where current is non-zero. Now the question arises that in which region we shall operate MOSFET in analog circuit when we are designing analog circuit. So we have two possible regions. The transistor may be operating in linear region or transistor may be operating in saturation region. So the question is in which region we would like to operate our transistor, say when we are designing an amplifier.
Saturation region.
In saturation region, the answer is correct. So can you tell me the reason why we want to operate transistor in saturation region?
Because in saturation, then voltage transfer characteristic is linear.
In saturation region, voltage transfer characteristic is
Linear.
okay. Let me plot the ID-VD characteristic. So this is ID-VD characteristic for certain value of VGS, right? And you can identify different regions of operation on this ID-VD characteristic. You know now this whole characteristic, this whole current characteristic is not captured by any single equation. Do you understand that? On the y-axis, we have drain current of a MOSFET. You can let's consider that okay, we have this N MOSFET. We have this N MOSFET, right? So this is drain, this is source, This is gate. We have applied proper biasing, and then we have certain fixed value of VGS, and we are sweeping this VDS. So this is the ID VDS characteristic. Is it correct? Or do you want to correct me? You may have come across two such characteristic. Okay, let me try to draw a straight line. You may have come across two current voltage characteristic of a MOSFET. One characteristic is the red one that I have drawn. Another characteristic, I am I, I am just drawing it, and you tell me, is it correct or do you want to make some changes? So this is for certain value of VDS. So in the first characteristic drawn in red, on the y-axis we have drain current, and on the x-axis we have VDS. And in the second plot, on the y-axis we have ID, and on the x-axis we have VGS. So this second plot is, I'm sweeping VGS and VDS is fixed. In the first plot, this one, I am having a fixed VGS and I am sweeping VDS. So is it correct or I have made some mistake? Can you tell me? We always have to deal with two current characteristics, ID versus VDS and ID versus VGS. So this characteristic is also referred to as ID, VDS, and this is referred to as ID, VGS. Do you agree with me, or it shall be the other way around? Anybody?
डोंट फील शाय, जैसा भी समझ में आए कुछ बोलो, इंटरेक्शन इम्पोर्टेंट है.
At times I may be wrong, so you you shall means feel free to share your view. In fact, you shall stay alert. If I am doing something wrong, you just interrupt me.
Yes, correct. It's right. Characteristics.
Okay, so it is correct now. Fine. So let us first discuss this ID VDS characteristic. This is very important characteristic. Now here you can see that VDS going from 0 to certain value, say the highest value is VDD, for example, in the circuit. So which of the above two equation represents this characteristic, ID VDS characteristic?
Linear.
The whole characteristic, the whole range of current, the whole range of ID VDS, which of the two equation represents the whole range of ID VDS?
Yes, saturation current equation.
So none of the, no single current equation actually captures the whole ID VDS range. You know that this is the saturation region and this is linear region, right? So in this linear region, the current IDVD characteristic is captured by this linear current equation, and in this saturation region, this IDVD characteristic is captured by the saturation current equation. So actually, no single current equation captures the whole IDVDS range. It's actually combination. This up to this point, it is the current is actually represented by, or the current characteristic is captured by this equation, and when it is in saturation region, the current characteristic is captured by the saturation current equation, right? Now in this saturation current equation, if we see, uh, so means we are or ideally what we want actually, that the current is independent of VDS, which is currently being represented by this current equation, saturation current equation. You do not see any VDS term here. In this saturation current equation, you do not see any VDS term here, right? Right. Now, but in reality, what happens, the current do changes slightly by VDS when VDS is increasing. So the red curve in saturation region is actually the ideal saturation current, where it is independent of VDS. That is what you see now. It is independent of VDS. And practically what happens actually, ID slightly increases when VDS is increasing. And so right now the saturation current equation does not capture this behavior. So how this behavior is accounted for in the saturation region? What modification is made in the current equation?
Multiplying the equation by 1 plus lambda VDS.
Yes. So you shall understand that this is actually a correction factor 1 plus lambda VDS, that term is added into saturation current equation to account for this non-ideality. This green one means the current of MOSFET is increasing with VDS. It is actually non-ideality. We do not want this, but it exists. So this is actually non-ideality. In ideally, when the MOSFET is operating in saturation region, the current shall be independent of VDS. And that is what we had written earlier, the red part of the saturation current equation. There was no VDS term, and it implies that in saturation region, the drain current is independent of VDS. But as we know, no ideal thing exists. So what actually in reality what happens, when VDS is increasing, the saturation current do increase slightly with increase in VDS. So it requires that a correction factor must be added into the saturation current equation to account for this increase in drain current with VDS. So that correction factor is this 1 plus lambda VDS. This is actually the correction factor to capture this non-ideality in the saturation region. And what this lambda is referred to as? This lambda is referred to as?
Channel length modulation.
Yes, channel length modulation parameter. Channel length modulation parameter. So actually, when VDS increases, the effective channel length is modulated, or to be straight forward, the effective channel length actually decreases, because what happens? Can you tell me what happens actually? This channel length modulation effect. What is this channel length modulation effect?
So the channel existing of electrons between drain and source is shortened after we cross a certain threshold voltage, and as we increase VDS, this channel shortens, increasing the ID saturation.
Yes. So as the name suggests, channel length modulation means the effective channel length, it is modulated with a change in VDS. And actually what happens when VDS increases, the effective channel length decreases. And if you see the current equation, so the red part of this current equation, we are assuming that the length remains constant, the effective channel length remains constant irrespective of VDS. But as we just saw, that in reality what happens when VDS is increasing, the depletion width at the drain channel junction increases. The junction is reverse biased. Do you agree? Drain body junction is always reverse biased. Say yes or no in a MOSFET.
Yes, sir.
For example, if this is the body terminal, so for N MOSFET, what you do, the body terminal is always connected to the least voltage available, least voltage. So if you are using a single power supply, means you are using VDD and ground. So the least voltage is ground. Therefore, the body of N MOSFET is connected to ground. Now, drain will always have a voltage which will be greater than 0, and therefore the drain body junction will be reverse biased because N MOSFET drain is N type. Can you recall? Body is P type. Can you recall? For an N MOSFET, the drain is N type and body is P type, right? So drain is N type, body is P type. So you have a drain body junction, and then you can see that the N type is at a higher potential than the P type. So the junction is reverse biased. Do you agree? So the drain body junction is reverse biased. Now you have learned the diode, na? So the same diode, this is PN junction. So what happens to the depletion width of a diode when you increase the reverse bias voltage? The depletion width increases. See, you are not able to recall. So say this is body, this is N plus source, this is N plus drain, and this is P type body. So there will be a depletion region, no? Whenever you have an N type silicon and P type silicon, so there will be a depletion region.
Yes, sir.
And this is actually the channel length. So what happens when the drain body junction is reverse biased, there will be the depletion region. And when this drain voltage is increasing, what does it mean? That the reverse biased voltage across the drain and body is increasing, and therefore this channel length, this depletion region is width is actually increasing. So what will happen actually, the effective channel length will be lesser and lesser. Okay. So, and that actually results into this increase in the current. Now to account for this, either we make this length VDS dependent, right? We have two possibilities to account for this increase in saturation current with VDS. As we see from this structure cross section of the device, that with VDS, the effective channel length is decreasing. Whereas in the current equation, we assume that this channel length L is fixed, independent of VDS. So to account for this non-ideality, we have two possibilities. Either we make this length VDS dependent. So we need to replace this fixed length by a channel length which is VDS dependent, or we keep this length fixed and add a correction factor 1 plus lambda VDS. Right? So this 1 plus lambda VDS is actually a correction factor which takes into account the effect of channel length modulation effect. And lambda is referred to as channel length modulation parameter. Is that clear?
Yes, sir.
So now we have a IDVDS characteristic. So actually, to understand this IDVDS characteristic is very important, because that gives us intuition where to bias transistor. So here I am drawing this current characteristic where the current is slightly increasing with VDS. Now we have already identified that this is linear region, and if this is, say, VDD, the maximum or the highest voltage, so this is saturation region, right? Now the question, we return to the initial question. The question was that in analog circuit, the transistor is always on, so ID is non-zero. Now we have two region of operation of a MOSFET where ID is non-zero. One is the linear region, another is the saturation region. Now, which of the two region we shall bias our transistor? Suppose we want to design an amplifier. So where shall we bias our transistor? Means both linear region and saturation will or satisfies the requirement that ID is non-zero. So where shall we bias our transistor? Saturation region or linear region? So to make a decision on that, let us talk about the intrinsic gain of a transistor, which is given by GMRO. Have you come across this parameter? GMRO.
Yes, sir.
GMRO of a transistor is actually a characteristic parameter of any technology node. So if for a given technology node, GMRO is higher, it implies that using that technology node, you can design amplifiers that will offer you higher gain. So GMRO, when you are designing an amplifier, GMRO of a transistor actually gives you an idea what order of gain you will be able to achieve. So suppose you have different technology node. So a technology node which offers you higher value of GMRO, that is higher value of intrinsic gain, implies that that technology node will offer, when you design an amplifier using that technology node, it will offer you a higher gain, right? Now GM, you know, GM is nothing but dou ID upon dou VGS, right?
Yes, sir.
Okay, so we will actually have since ID, you can have a ID linear or you can have ID sat, therefore you will have GM linear and GM sat. ठीक है ना? अगर आप इसको एस्टिमेट करेंगे लीनियर रीजन में, सो दैट विल गिव यू GM लीनियर, और इसको एस्टिमेट करेंगे सैचुरेशन रीजन में, इट विल गिव यू GM सैट. अभी तक हमने ये तो डिसाइड कर नहीं पाए हम लोग कि मॉसफेट को हमें लीनियर रीजन में ऑपरेट करना है या सैचुरेशन रीजन में ऑपरेट करना है, राइट? But if you, let us talk about GM, if you go back and see the current equation, so if you differentiate this ID linear with respect to VGS, you will get GM, which is a function of VDS. Do you see that? Can you contemplate that if you differentiate this current equation in the linear region with respect to VGS, you will get an expression which is dependent on VDS.
Yes, sir.
Right. So what happens actually, GM linear that becomes VDS dependent, that becomes VDS dependent, right? Okay, let us go to the saturation region. So when you differentiate this expression, the saturation current expression with with respect to VGS, you will get this GM, the outcome, which will depend on VGS minus VTH, means you have a VGS term or overdrive voltage term, and you will also have this VDS term, but you can see that this VDS appears as a multiplication with this lambda, and lambda is always less than 1, right? So in saturation region, what happens, this GM actually is a very, very weak function of VDS, and actually when we write GM expression, we in fact ignore this dependency, lambda VDS. And we have this knob with us, VGS minus VTH, which is also referred to as the overdrive voltage. So using or setting the appropriate value of overdrive voltage, we can actually tune the GM, right? So you can adjust GM sat to a desired value using VOV. Using VOV, you can adjust GM in saturation region to a desired value. Whereas here you do not have that knob to adjust it, and it also is VDS dependent, which is detrimental, which is undesirable, right? So from GM perspective, this seems to be appropriate, right, which is independent of VDS, GM sat, which is independent of VDS, and you can also tune it using this knob overdrive voltage. Let us so we have discussed this GM term. Let us come to this RO term. Okay, so RO will be actually what? RO, the small signal parameter RO, is given by do you agree?
Yes, sir.
So now can you tell me which of the two region, linear and saturation, will offer you a higher value of RO? We want this to be higher, no? As I told you that the intrinsic gain of a transistor is very important characteristic. A higher intrinsic gain, a transistor, when we design analog circuits, so let's say amplifier, when we design amplifier with a transistor that offers you higher intrinsic gain, implies that the amplifier will offer you higher gain. So from GM perspective, it seems that the saturation region is favorable. Saturation, we shall bias transistor in saturation region, right? Because it is independent of VDS. It is independent of VDS, and we have a knob overdrive voltage using which we can tune it to a desired value. Now the second term in this intrinsic gain is RO, which is given by this RO is equal to 1 upon dou ID upon dou VDS. Now I'm asking you, from RO perspective, which of the two region of operation is favorable? इंटर्नशिप शुरू हुआ, मैं आता हूँ आपके पास। कोई नहीं, मेरे को फोन पे बुला लीजिए। नहीं, मैं आ रहा हूँ 20 मिनट में आ रहा हूँ। So tell me
Saturation 1.
why.
As there is no term for the VDS,
Mhm.
when we differentiate with respect to VDS, we get the constant value which is less than the.
So if you closely see, yes, you are correct. If you closely see, this dou ID upon dou VDS is nothing but the slope. Slope है ना? ये slope
Yes, sir.
और ये slope. तो ये तो देख करके हम बता सकते हैं कि किस रीजन में स्लोप जो है, इस कर्व का स्लोप किस रीजन में ज्यादा है. किस रीजन में ज्यादा है इसका स्लोप?
No, linear.
Yes, slope is steeper in linear region and slope is smaller in or gradual in saturation region. So since the slope appears in denominator, so higher slope means lower RO and lower slope means higher RO, right? Therefore, RO in saturation region will be much higher as compared to the linear region.
Yes, sir.
Right. So now we can conclude that from RO perspective also, saturation region is the favorable region. Because we always want this product to be as high as possible. It is a characteristic parameter of any technology node. When you have to select a technology node to design analog circuit, this intrinsic gain of transistor in that technology node is a very important characteristic parameter that we shall look for. A technology node that offers you higher intrinsic gain transistors will offer you a higher gain when you design amplifiers using that technology node. Is that clear? So from this discussion, we can actually conclude.
Sir,
Yes.
uh, so what's the problem with the VDS dependent GM linear view?
So can you recall when you design amplifier, at what terminal you take the output from?
So at drain.
At drain. So when you write this gain is equal to GMRO, and this, if this GM is so you are taking output from drain which is having, say, swing, higher swing.
Yes, sir.
The output when you are designing an amplifier, so input will have a small swing and output will have, of course, much larger swing. So when the drain voltage is changing by a large amount, what will happen to GM?
GM will change also.
GM will also change by a large amount, and then what will happen? The gain itself is not constant.
Okay, sir.
Right? We want these parameters to be constant so that we have linear relationship between input and output.
Okay, sir.
Right? So the conclusion is bias MOSFETs in saturation region. For designing analog circuits. Right. Is that clear? Anybody having any query?
No, sir.
So from this discussion, we have concluded that when we have to design analog circuit, so now we are sure that we want to bias the transistor, we want to operate the transistor in saturation region. Now there is no doubt about that. Okay. Now what the next thing that we want to do is extracting MOSFET parameters. You see the current equation in saturation. So I will write now, okay, I shall write ID sat rather. Later we will use only ID term. But for today's, I shall write ID sat is equal to half mu C ox W upon L VGS minus VTH whole square. Okay. And we most of the time what we will do actually, that 1 plus lambda VDS term will be dropped. So okay, so now the parameters, the MOSFET parameter, so you see W upon L is actually design parameter. What do we mean by design parameter? That a designer actually, so this W upon L and this VGS, they are design parameter. Whereas this mu Cox, this VTH, they are process parameters. This is also process parameter. So this lambda actually, of course, is technology dependent, but we can tune it using what MOSFET parameter we can use to tune it, or I shall say which design parameter I can use to tune this lambda channel length modulation parameter. So channel length L. Ideally, we want this lambda to be what? Infinite or zero?
Zero.
Yes. Ideally, we want this lambda to be zero. So when the lambda is zero means there is no channel length modulation and you have an ideal saturation current equation. But practically it is not zero. However, this lambda is inversely proportional to the channel length. So as you increase, or when you use a long channel device, this lambda will actually be smaller. So of course, for a given channel length, this lambda is also a process parameter, but you can tune it using channel length L. Okay. So now we have to actually extract these MOSFET parameters. Let's say how we can extract this mu Cox and this VTH of a transistor from its IV characteristic. So for that, let me draw. So let me rewrite actually this equation with certain approximation. So I can write ID sat is equal to half mu Cox W upon L VGS minus VTH whole square, or I can write it like this: square root of ID sat is equal to square root of half mu C ox W upon L and VGS minus VTH, which can also be written as VGS minus VTH is equal to half of 1 upon half of mu C ox W upon L and a square root of ID sat, right? Do you agree? Writing this saturation current equation like this, and if you are thinking that why I have not used that 1 plus lambda VDS term, so that term has been dropped as an approximation to simplify the calculation. We always make such approximations. So as an engineer, we always look for a trade-off between the computational complexity and the accuracy. So we make approximations to simplify the calculation while not compromising with the accuracy too much. So when we have written the current equation like this gives an idea how we can actually extract the threshold voltage of a transistor using ID-VGS characteristics. So you have ID. Now when you have ID, we can also, or okay, let me plot first ID so that you can see. So suppose this ID, so you will have, say, like this ID like this. But the equation that we have manipulated like this, we have written this equation like this, where VGS minus VTH is equal to half, and then this term, this constant term is there. Of course, W upon L we have fixed, and this square root of ID sat is there. So if you take the square root, you can easily plot it any tool, and in LTS Spice also, you can plot a square root of ID. So a square root of ID will actually look like this. Like this. So from here, you see, and on the x-axis you have VGS. So what happens if this VGS minus VTH is 0? The current will be 0, or you can say that the current is 0, the current square root of ID is 0. This implies ID is 0. Okay. So what will happen actually? VGS minus VTH will become 0. Do you agree? We have plotted this square root of ID on the y-axis, and you have VGS on the x-axis. Now a square root of ID 0 implies what? VGS minus VTH is equal to 0. Do you agree?
Yes,
so
sir.
what actually you can do, if you extrapolate this ID characteristic and it hits the x-axis here, and this axis is nothing but ID is equal to 0, or square root of ID is equal to 0. Let's say, write it like this, right? So this point is what? From here you can write, no, VTH is equal to VGS when ID is equal to 0. Do you agree? Do you agree with that? How to
Yes, sir.
extract threshold voltage from ID VGS characteristic? So to extract threshold voltage from ID VDS characteristic, what you can do, you can plot a square root of ID versus VGS, and you see this equation. You see this equation. So what happens when, so again, when I am writing this equation, do you think that this equation captures all the red characteristic that is shown over here? Is it like that? Is my question clear? जैसे हमने ID VD कैरेक्टरिस्टिक में देखा था कि not the whole range of ID VDS was captured by any single equation. Similarly, on the ID VGS characteristic also, do you think that the whole current voltage range is captured by, can you tell me, means where is the linear region and where is the saturation region? Any guess? On this ID VGS characteristic? आप देखो ना, ये जो इक्वेशन है, अगर आपने इसको ऐसे प्लॉट किया है तो ये देखिए यहाँ पे ये लीनियर रिलेशनशिप है नहीं है इन दोनों में, है ना लीनियर रिलेशनशिप?
Yes.
और वो that linear relationship is actually valid for this region, not the whole region, only this region for example. ठीक है, यहां भी जैसे देखें रेड पार्ट को देखें अगर, तो इसके इस तरफ तो लीनियर रिलेशनशिप ये वैलिड है, इसके लेफ्ट पार्ट पे तो नहीं है ना वैलिड. सो एक्चुअली हियर द ट्रांजिस्टर इज ऑपरेटिंग इन लीनियर रीजन और हियर इट इज इन सैचुरेशन रीजन. जब सैचुरेशन रीजन में है देन दिस लीनियर रिलेशनशिप इज वैलिड. स्क्वायर रूट ऑफ आईडी ये फिक्स्ड एक मल्टीप्लिकेशन टर्म है. हियर यू हैव VGS माइनस VTH. तो अब आप ये जो लीनियर पार्ट है उसको एक्सट्रापोलेट करेंगे तो इट विल हिट द एक्स एक्सिस समवेयर हियर, and at this point what happens, the ID is 0, and for ID is equal to 0 VGS minus VTH is 0, and therefore this the point where this line hits x axis, that value of VGS represents VTH. Think about it. Am I clear?
Yes, sir.
जब आपने स्क्वायर रूट ऑफ आईडी लिख लिया यहाँ पे इस तरह से, तो अब ये VGS माइनस VTH और स्क्वायर रूट ऑफ आईडी के बीच में लीनियर रिलेशन आ गया ना. लेकिन ये जो लीनियर रिलेशन वैलिड है वो सिर्फ सैचुरेशन रीजन में ही तो वैलिड है ना. यहाँ पे ट्रांजिस्टर सैचुरेशन में नहीं है. तो ये जो लीनियर पार्ट है इस कर्व का, ये जो लीनियर पार्ट है उसका जब एक्सट्रापोलेट करेंगे आप, इट विल हिट एक्स एक्सिस समवेयर हियर. नाउ at the x axis the value of current is 0. Now when you put value of current 0 in this equation, we get VGS minus VTH is equal to 0. What does it imply? That VGS is equal to VTH. What does it mean? That when that value of VGS, for which a square root of ID is 0, ये जो इसको जब एक्सट्रापोलेट कर रहे हैं, that value of VGS is actually the threshold voltage. Do you agree?
Yes, sir.
हाँ, क्या कह रहे हैं? कोई और भी कुछ कह रहे हैं? Please be a little louder. Anybody having any query?
No, sir.
Okay. So now what you need to do, because I will stop here today and I'm giving you a small task. I have already shared LTS Spice simulation setup and the TSMC 180 nanometer technology node file. And I hope that all of you are familiar with the LTS Spice. You have already used LTS Spice. Is there anybody who has not used LTS Spice earlier? If all of you are from AMU, I'm sure all of you have used LTS Spice earlier. So anybody from outside AMU, from outside AMU, other institute. So you may not have used LTS Spice or Spice simulation, but if you are from AMU, I have no doubt that you have used LTS Spice earlier. So what you have to do, so you shall go and use plot the ID VDS characteristic for a transistor with 360 nanometer length and 1 micrometer width, and you shall plot, and of course you shall use VDD is equal to 1.8 volt, and using that you shall plot a square root of ID versus VGS characteristic and extract VTH threshold voltage of okay. So I think there is no query. So that is the exercise that you shall do and post your screenshot of the square root of ID versus VGS and the estimated value. You can actually label that screenshot itself. So you can actually label it like this when you have plotted it like this, and then so you can label it this point itself with the value. Okay, VTH is equal to whatever value you are getting. So you can label. So you just post one screenshot. I will create an assignment and you just post your screenshot of the simulation result that you are getting. So that's it for today. If you do not have any query, I will close the class now.
Please share this presentation.
This presentation, I don't think, is there anything that, okay, I do not have any issue. If you can make out of something, it means अभी आपने जो लेक्चर सुना है उसके अलावा अगर इसको रेफर करना है ठीक है, मैं शेयर कर दूंगा, नो इश्यू. But it looks like very cluttered. Anyway, any other query regarding the
Sir,
internship?
sir, always the class timing is 10:30.
No, I cannot guarantee that because I am occupied with some other departmental work also. So sometimes it may be that the class time is changed, but I will try my level best to keep it at this time only. Does that okay with you? Is that okay with you?